like I was mentioning, the first week and a half or so is basically going to be a whirlwind review of the basic chemistry that you need to know that we're going to be building on for the rest of the semester. So let's do that. The level of the chemistry that you do in physiology is different than in chemistry. You're not going to have like, be answering questions where you're having to figure out distribution of electrons and which orbitals on, some atom or something. It's going to be more like what kind of bonds are these things making, or what kind of reactions are these things going to have based on what kind of molecule they are. What dissolves in water or not, that's going to be huge. We're going to talk a whole bunch about what makes something hydrophobic or hydrophilic, because that's going to be huge. Everything in the body is got to dissolve in water or some way or another get into the plasma to get transported around. So it makes a big difference if things are, hydrophilic, they like water, they dissolve easily, or hydrophobic, like, oil, it separates. So we'll talk a bunch about that. Clipboard. Okay, energy and matter. So kind of the two basic things. Obviously, if you get into E equals mc squared, they're interconvertible or this or that. But for our class, we're going to talk about energy and matter as kind of separate things. Let's just briefly talk about energy. Let's start with the energy because we can cover that quickly, and then we'll get into the matter and atoms and molecules and bonds and all that. So we're going to start with energy. Basically, kind of the ability to do work and stuff. What are the two basic forms of energy that we talk about?
Heat and kinetic.
Say it again.
Heat and calories.
So calories is a measure of energy. That's a unit that will tell you how much energy is there, but it's not like kind of a form of energy.
I forgot.
Kinetic.
Kinetic.
So we talk about kinetic energy, energy of motion.
Chemical.
And potential.
Chemical energy is a subtype of potential energy, which is basically stored energy. So kinetic energy is when things are moving, like when your little molecules, like the myosin heads in your muscle, are changing their shape and pulling and making your muscles get shorter. Kinetic energy is just anything that's moving and it can do some kind of work as it, impacts something else. So obviously, it's got some energy as it's stored in that motion. You get 1/2 mv squared, if you remember that stuff. It's like physics. Potential energy, this is stored energy. This is energy like in a spring, right? You take a spring and you squeeze it down and it's not doing anything. If you're holding it there really tight, but there's energy stored in the coils of that spring, and if you let it go, it like boing, springs out and can do something. So let's focus in. Potential energy is going to be really big in this class. Let's focus in on the different forms of potential or stored energy that we're going to be seeing as we go through. What are the different ways that energy gets stored that we can then release and do something with?
Chemical, mechanical.
So one is chemical. Chemical is where you have energy stored in chemical bonds. And when you rearrange those chemical bonds, usually through some kind of a chemical reaction, energy gets released. Like a classic example is, gasoline in your car, right? You put gasoline in your car and it's got these octane molecules that are then get combusted, releasing the energy in those molecules. And you've got energy turning into kinetic energy, rolling your car across the bridge and going to school or something. So chemical energy, stored, in chemical bonds. Again, like a class, or gunpowder, right? Here, in fact, party snaps, right? You've got like this little thing, you've got like some little gunpowdery thing on the little rocks on the party snap. I squeeze it, boom, like I just released that energy. It was stored in the bonds and then it went, it was sound and light, right? That's stored energy, which then I released and did something with. So it can be stored in bonds like that. No, I got crap all over my iPad. Hold on a sec. The thing you often see as chemical energy is what's the classic molecule, the currency of energy that we use in our bodies.
ATP?
ATP is going to be a classic example, right? We're going to have, ATP, which is adenosine with 3 phosphates hanging off it. And there's energy stored in the bonds of that ATP. And if you break it apart, ADP, which is adenosine with 2 phosphates, D is di, plus the P, you usually do P sub I, it means inorganic phosphate. It's a phosphate no longer attached to a carbon containing molecule. And it releases energy. So we have stored energy here in the ATP. We can release that energy when we break it apart into ADP plus inorganic phosphate. And it's really easy to couple this reaction to other reactions that need energy. So you can release energy from this reaction and then use that to drive other things. This is going to be a really common way to get energy that we need to run things that require energy, the stored energy of ATP. Obviously sugar, right? Sugar's got a lot of stored chemical energy in it. And that's glucose. This is going to be the main fuel for cellular respiration. By dismantling the bonds of this glucose, we're going to release the energy that we then turn into the ATP, which is a more easy to use version of stored chemical energy, which we can then use to drive all sorts of things in the cells. But again, this is basically fuel, it's energy, it's like gasoline. You can break the bonds, release the energy, and do something you want. Another common form of chemical energy that we're going to see is in high energy electrons. The basic way to think about it is, I think of the analogy of gravity. Like if I can take something like a stapler, and the higher I lift it up high, the more energy it has with respect to gravity. And as it falls, it can do more work as it falls down back to the ground. So this stapler, how much energy does this stapler have? It depends on how high it is up above the ground or close to the ground, right? So the same stapler can have a lot of energy if it's up way high. It might not have very much energy at all with respect to gravity if it's right near the ground. Or if it's lying on the ground, it has 0 energy with respect to gravity. So like the electrons in your atoms is kind of similar, depending on how the electrons are configured. They might have a lot of energy or not as much energy. So like a classic. So, electrons. And electrons usually you draw as like an E minus. It's an E for an electron, a minus because they got a minus charge. So we have this high energy electron carrier, NAD plus. So high energy electron carrier, this would be if it is not holding on any electrons. NAD plus can grab on, it needs another hydrogen and it needs 2 electrons. It becomes NADH. This has these high energy electrons. Like if you see an NADH, you're basically looking at something that's got a lot of stored potential energy. And when it donates those electrons to other things in these redox reactions, that energy gets released. Just like if I have something up very high up off the ground and I start dropping it to lower things, if I have maybe a water paddle wheel here in the flour mill, and there's a bunch of water up in the reservoir here, and then I'm running the water down the hill from high to low with respect to gravity, and now my paddle wheel is spinning around as the water flows down. I'm getting work out of that energy of the water flowing from high to low. It's kind of the same analogy. It's a good analogy for thinking about these high energy electrons getting handed down to positions where they're in a lower energy configuration, and you can capture that energy to run things in your cells. So like, it's going to be an essential part of cellular respiration, which we're going to look at in more detail. We're going to see NADH and its relative FAD doing this job of storing energy as high energy electrons, handing those off in these redox reactions and releasing energy to drive other parts of the reactions. So ATP, NADH, those are really common molecules we'll see that store potential energy. Like I said, glucose, classic, storing potential energy that we're going to be using a bunch because it's the main field for cellular respiration. So potential energy stored in chemical bonds. And again, we'll come back and look at this in much more detail as we go into specific examples. What other ways do we store potential energy?
Mechanical.
Mechanical, exactly. I mean, that's kind of like that spring I was talking about. You know, for instance, a spring, right? You take a spring, and if you squish it down, it's now got stored energy. It's still not doing anything, but if you let go of that spring, it can turn that stored energy back into kinetic energy of motion as it unsprings. In your body, we have examples of this. For instance, in Bio 110, you've talked about, muscle contraction and the myosin heads bending, and myosin, it's a molecule. It's a big protein, and it has different conformations. You can have like it's kind of sprung conformation, or you can have kind of like this cocked conformation, right? It's like, it's here, it actually is going to take the energy of ATP to bend this thing, and it gets stuck in this thing. And then with the right trigger, boom, it will unfold. And that's going to be, actually, it's the other way. Now I'm being a spaz here. This is cocked. This is sprung. So as it springs here, it's going to pull, it's going to shorten your muscle. So you're going to convert, again, that stored mechanical energy in this myosin molecule into kinetic energy, moving your muscles around. So mechanical energy is going to come up as, or stored mechanical energy, stored potential energy will be important in the class. What are other ways to store energy?
Batteries.
So that would be, okay, so it's an electrical gradient. So let's get there. So a gradient means where there's kind of an unequal amount as you go across space. Normally you think of things being kind of homogeneous, being equally distributed everywhere. An electrical gradient, let's say there were more positive charges over on this side and more negative charges over on this side. So now, if you put something, what's that? What is a charged atom? What do we call a charged atom?
Ion.
Ion. So let's say we take an ion. Let's say I take a potassium ion, a K+, and I put it in this electrical gradient. What's going to happen to it? Where's it going to go? What kind of forces will be on it?
It's going to go to the negative side.
It's going to get pulled over to the negative side. It's going to get attracted to the opposite charge. And how strongly it's getting pulled there is going to depend on how steep this gradient is, how negative it is compared to the place where it is. So this is another way to store energy, is by having this unequal distribution of electrical charge. We're going to look at this in much more detail. This is going to be critical in cell signaling and how neurons work and how muscles work and all that. We call this electrical gradient, this potential energy, voltage. Voltage is electrical potential energy. When we talk about there being a voltage across the two sides, that means that there's this charge imbalance that's going to make some other charge want to move from one side to the other. The higher the voltage, the stronger that force is against this thing to move it from one side to another. Right, so when you stick your light on your battery, it's basically causing electrons to flow through the circuit driven by that electrical potential energy. Sometimes people call it like electrical pressure. Right, because it's kind of this pressure pushing or moving, it's more pulling, I guess it's pushing and pulling the charges to move. So you can have potential energy stored in electrical gradients. That's going to be essential to understanding how cells, particularly excitable cells like neurons and muscle cells, do their thing. So we'll be spending a lot of time getting down into the details of voltage and how it affects forces on ions. What's another way to store potential energy?
Thermal energy?
So there's thermal. Thermal is more kind of the randomness. It's worth knowing that thermal energy exists. Let's talk about what actually, let me get back there. It can be potential if you're like kind of moving from hotter to cold, but let's get back there later. Heat is kind of this more generic thing that we will talk about.
Is it passive? Is there?
So I'm going to concentration gradients.
No, generator.
So concentration gradients, so chemical concentration gradients. If I have, a whole bunch of stuff dissolved on this side and not that much dissolved on this side, what's going to happen?
It's going to balance out.
So there's going to be this net movement where things go from high to low concentration. What do we call that process?
Osmosis or diffusion?
This would be diffusion. Diffusion is going to be a super important concept throughout this till the very last day of the semester. In osmosis as well. Osmosis is a special case of diffusion where it's the diffusion of water across a semi-permeable membrane. We're going to be looking at diffusion and osmosis in excruciating detail. We have like 6 hours of labs just going into depth in osmosis and diffusion, trying to make sure you get a really good sense and intuition about them, since they're so kind of foundational to everything that's happening in the body and how things are moving across membranes and things like that. So these chemical concentration gradients, if you have a lot of stuff dissolved on one side, not much on the other side, there's going to be this net movement. And the net movement is due to just the intrinsic energy of things. So let's get back to this idea of what is heat. What does it mean if something is a higher temperature or a lower temperature? What does it actually mean on a physical level in terms of molecules,
Is
atoms?
it higher or lower kinetic energy of the particles?
Yeah, exactly. So this is, you have, we call translational, meaning moving through space. Things are zipping around. There's vibrational, where you have something kind of like, especially if you have like two atoms connected in a bond, sometimes they're a little further, sometimes they're a little more squished. They're going, grrr. You have rotational, where like, you know, so they can either go back and forth like that, or rotational around their bonds, or translational, the whole shebang is moving through space. So, and the higher the heat, when we say something is hotter, it just means there's more of this energy. Things are vibrating even more and zipping through space faster and farther. So that's what, so it's important to realize anything that's not at absolute zero, which is like 0 degree Kelvin, like minus 273 degrees centigrade, has this energy where it's zipping around and vibrating. And so diffusion is happening because it's not like magic. If I have like a higher concentration of, let's say these little dots are just supposed to be whatever, some molecule. They are all on their own, just zipping through space in random directions. They are not, they don't have any like real, at least in the our construct here, they don't have any real consciousness or desires or anything. They're just little particles that are moving. But if they are moving in the direction where it's a higher concentration, it's much more likely you're going to hit something and then bounce off in some other direction. Whereas if you're going in this direction towards the lower concentration, you're probably going to go much farther before you actually hit something. Right? So if we actually step back and look at it, there is going to be a net movement of the particles from the higher concentration to the lower concentration. Right? It's kind of, if you had a bunch of kindergartners and you had them all drink Red Bulls, and then you kind of rope them in the corner of the room, you know, and then all of us, so you have this high concentration of these totally like
Spitting on the court, man.
little kids
Terrible.
in the corner, and the rest of the room is kind of empty. And then you unleash them, and they're not thinking like, oh, it's crowded here, and they're just like bouncing off of everything. But there's going to be a net flow of little kids from this really tight concentration to where there's more space to just sprint without running into something and bouncing off of something, right? That's what diffusion is like. You know, we say diffusion is a type of passive transport because you don't have to add energy to it to make things move. But it wouldn't be happening if the molecules didn't have some intrinsic native energy to start with. Otherwise, they would just be lying there, right? So energy can be stored in a concentration gradient. When you have a concentration gradient, there is going to be this tendency of things to move from high to low concentration. Right. Again, we're going to come back and visit diffusion in much more detail as well. It's good.
Professor,
Uh-huh.
I don't know if it's necessary or not, but can you maybe give me a definition or how you would explain in another term, net movement?
Net movement. That if you look, so net means kind of after you do the balance sheet. So there's going to be things moving from one side to this side. There's going to be other ones moving from this side to this side. If I say there's net movement from high concentration to low concentration, when I kind of do the final balance, there will have been more particles that ended up moving from high to low than ones that moved from low to high.
Okay, thank you.
Yeah, so there's just because we have a net movement this way doesn't mean that there aren't some that are actually moving the opposite direction. It's just at the end of the day, way more moved from high to low than low to high. So we'd say there's a net movement. More, yeah, in general, things moved from high to low. Yeah.
Can I ask a question as well?
Sure.
So just with I understand like how the concentration gradient stores energy. So that's going to be mechanical, right?
No, it's more, it's the energy stored in a concentration gradient.
Okay, so it's sort of separate from mechanical or chemical. You just kind of call it its own thing.
Yeah, so mechanical energy is there's actually some physical thing that's kind of like, it's like a rubber band. There's some physical or a spring where this physical thing that's kind of putting under stress and then you let it go and it lets go.
Okay, so guys, I was sort of thinking like you were talking about like the kindergartners or something like holding the gradient together, like to start, but that's not.
Right,
don't
so
think we
that
like
would
that.
be like, what if, because something kind of created this imbalance in the first place. Once you let this thing run, eventually everything is just going to equalize and be homogeneous and there's no more gradient anymore. So something was kind of keeping this together and then we let it go.
Right. So I was thinking that like the something, whatever the something might be, was what in my brain was making me think it would be then mechanical, but I won't think that way. It's just, I'm going to put concentration gradient as its own thing.
Yeah, just yeah, for some reason, there is a higher concentration of this compound on one place versus another, and then we let it go. And also we should mention that this is different than most of the things that you have looked at in chemistry. In chemistry, you almost always look at things in equilibrium. This is decidedly not an equilibrium. That's why things are moving. Things are out of balance. So things are moving from one side to another. And if you let it go long enough, it will eventually reach equilibrium when we have an equal concentration on all sides. Then there will be no net movement anymore because there'll be just as many things moving one direction as the other direction. So that's in osmosis. Let me just put osmosis in here as really briefly. We're going to look at osmosis in way more detail, but I should just introduce it here since it makes sense because it's a special version of diffusion of what we've just talked about here. It's a special case of diffusion. So in fact, maybe I'll use my little typing tool so it will be what? Okay. Oh, there it goes. So it's the diffusion of water across a semi-permeable membrane. So the idea here, normally you don't think of water diffusing. You think of water as the stuff that the things are dissolved in. But in diffusion, we're going to have a semi-permeable membrane. Semi-permeable meaning, oh, you silly goose, hold on. I got to get out of the typer tool. There we go. So semi-permeable membrane, this allows water to move across. So it's semi-permeable. Water can move across, but then some other thing that we're interested in could be whatever. Some solute, something that's dissolved in the water. It can't move across. So semi-permeable membrane, it's a membrane separating two sides of some aqueous solution. Water can freely move across the membrane, but whatever solute is dissolved in the water is trapped and can't cross the membrane. So that's the setup for osmosis. And then we have to think about, well, what's going to happen to the water?
I'm not sure I understand.
Oh, my iPhone doesn't understand, so that makes me think maybe you guys don't, so I should explain it a little more. Let's see. I didn't say like, hey Siri, that's weird. So what is going to happen here is water now actually has an unequal gradient. You know, the side there where there's more solute, it's taking up space. It means there's less water on this side, and there's more, or I shouldn't say less, I should say high concentration. Let me get smaller. It's going to be kind of a lower concentration. Saying concentration of water is a weird thing. It's useful, I think, in trying to understand osmosis, but in general, you don't think about it that way. Think about concentration of some solute dissolved in water. That's why I'm putting concentration in quotes. But the reality is there is kind of a higher concentration of water on this side than this side. So what's the net movement of water going to be, given that the solute can't move? The solute is trapped.
To the lower concentration of water.
Yeah, so water is going to have a net movement going this way. Normally, if there was no semi-permeable membrane, what would be happening instead?
Diffusion.
Yeah, the solute would diffuse the other direction, right? If this is side A and this is side B, if there was no membrane, the solute would just diffuse from side B to side A. But in this special case with this semi-permeable membrane creating this weird situation where the solute is trapped, but the water can move, we end up getting a net movement of water from side A to side B instead. The kind of intuitive way for me to think about it is that the side that has more stuff dissolved, the kind of saltier side, kind of draws in the water. This is, I think, a much more intuitive way to think about osmosis, right? I don't know if you did it like when I was a kid before I knew better. It was kind of fascinating to sprinkle salt on a slug. What happens if you put salt on a slug? I don't know if kids still do this. Maybe it was
Not good. It like dissolves, foams.
it basically sucks all the water out of them. Right? This is why actually you use like salted and candied food to preserve it, because really high levels of concentration of solutes sucks the water out of things. Any kind of little pathogen that lands is going to go, the water is going to get sucked out of it.
It's like using salt on icy roads or on ice cubes. It'll start to dissolve it.
That's different. That's
That's
actually
different?
that's changing the melting point. So the
Right.
ice will melt at a lower temperature than it would have otherwise.
Oh.
This is about a net movement of water from one side to the other side of a semi-permeable membrane. So for osmosis to happen, there has to be a semi-permeable membrane that allows water to move from one side to the other, but does not let the solute move from one side to the other.
So just for clarification, it's the concentration is more, it's not the amount. When you say higher concentration, it's not a higher amount that's going to a lower amount. It's more the concentration of salt. Is that?
I'm not sure I understand your question.
So I guess intuitively, I would think from higher concentration to lower concentration, the water would flow, the net movement would be towards the lower side in order to balance
Lower what, right? You have to be more specific.
lower concentration.
Of what?
That's, I guess, what I'm saying.
Right, so I'm saying there's two ways to think about this. You can think about it, concentration of water, which is kind of wonky, but will result in the water moving, which is what's happening. But I was saying in a more intuitive way, when I personally think of osmosis, I think of the higher concentration of solute, the side that's got more stuff dissolved, salt or sugar or whatever, kind of sucking the water over, right? So,
Okay.
so in my mind, that's a more intuitive way to think of osmosis. Like the water gets kind of sucked into the area that has more solute dissolved.
Okay.
But if you want to but you can also kind of frame it this way in terms of like, quote unquote, concentration of water driving the water moving. So then it actually is kind of diffusion of water, which is what it is. But again, intuitively, it's really confusing to think about a concentration of water because that's not normally how you think about it. Normally, you think of concentration of some solute dissolved in water, the water just being the solvent. So any points of clarification here? We're going to be talking about osmosis a bunch. We're going to be talking about hypo and iso and hyper osmotic solutions and hypo and iso and hypertonic solutions and what that means and what sets that up and why that's so important as we look at all the processes in your cells. But for right now, I just want you to have this, this should not be new, right? Osmosis is, I know that they talk about this a bunch and you do experiments on this in Bio 110. So this is review, but it's important enough that I want to kind of make sure that you really get it, because if this doesn't make sense, lots of other stuff is not going to make sense as we go deeper. Any questions about osmosis?
I have a question not about osmosis, but just really quickly about heat. I know we already discussed it. So with heat, like I understand how heat works, but how did you want us to think about that in terms of this classification? Like,
just think of heat as just the native energy that all molecules and atoms have that is allowing diffusion to exist even, right? Diffusion could not happen if there actually wasn't some native motion of things zipping around to start with.
okay, so just basically understanding it as that it's what's making diffusion possible.
It's actually what's making chemical reactions happen as well, right? If molecules weren't moving around, they wouldn't be bashing into each other or tearing apart from each other. So you have to have this kind of native energy of the atoms and molecules so they actually bash into each other to have chemical reactions occur.
Okay.
So, and the higher the temperature, the higher the heat, the faster the diffusion or the faster the reaction rates. So you can think of it, it's going to be important when you think of things that drive reaction rates or drive diffusion rates. Higher temperature is going to be positively correlated with diffusion rate or with reaction rates.
Okay, got it. Thank you.
Okay, I want to make sure we keep on rolling on. So let's keep on rolling on. So that is energy. We have energy in chemical bonds, chemical energy like ATP, NADH, glucose, lots of other things, octane, gasoline, Pop-Tarts. There's lots of energy stored in the Pop-Tart that'll get you going. We have energy stored in mechanical systems, again, like springs, but also in like the myosin molecules in your muscles, as well as other things we'll talk about that act as actual physical ways to store energy. You can kind of like compress them and they'll spring out, or stretch them and they'll pull back. There's chemical energy, there's mechanical energy, there's energy stored in diffusion gradients. If you just have a lot of stuff dissolved on one side, not so much on the other side, you're going to have a net movement from high to low concentration, which we call diffusion. There's there's energy stored in electrical gradients, what we call voltage differences. There's more positive charge on one side and negative charge on the other side, then if I am an anion, some negatively charged thing, I'm going to get pulled over to where it's more positive. Or if I'm a cation, a more positively charged thing, I'm going to get pulled over to the side that's more negative. Again, when we get into resting potentials of cells and neurons and how that all works, we're going to see you often can have opposing a chemical force. The diffusion force might pull things one way due to its concentration gradient, might pull it the opposite way due to the voltages, the electrical gradients, and they are going to find some balance, some equilibrium that's going to end up creating these equilibrium situations, and we'll get to the resting potentials of our neurons and our muscle cells and things like that. So all these things are going to start all interplaying with each other. So let's go now to matter, like the stuff. You know, gas, liquid, solid. You know, obviously, you know, if you're in chemistry or physics, there are other forms. There's plasmas and this and that. So don't worry about, in our class, things are either going to be a gas, a liquid, or a solid. And matter is going to be ultimately made up of atoms. So we should talk a bit about atoms, and then we're going to be able to hook up atoms with chemical bonds to make molecules, right? But let's start with atoms. And again, the level you need to know this for this class is relatively basic. But let's talk about what is an atom. So actually, I'm going to stop this for a second just to clear out all my whiteboards. So what are the parts and pieces that make up an atom?
Proton, electron, neutron.
Yeah, the protons, electrons, and neutrons. If you go deeper into chemistry and physics, there's lots of subparts of those. So don't worry about that. We don't need to think about any of the deeper levels of what is an electron, proton, or neutron. For our class, it's fine just to think about them as the basic building blocks. You know, in the nucleus of an atom, you're going to find protons and neutrons. Protons are always +1, neutrons have neutral charge. And then zip it around, you have electrons. So this is an atom. What determines what kind of element, what atom this actually is?
Number of protons.
The number of protons. So the number of protons we call the atomic number. In fact, it's worth going over to this for 1 second. So, here are the classic periodic table of the elements. So it is important that you understand the basics of this, right? The little number up in the corner here, this is the atomic number. This is saying if I have something, no matter what else is true about some atom, if it has 11 protons, it is a sodium. If it has 6 protons, it is a carbon, no matter what else. If it has 17 protons, it is a chlorine, no matter what else. So that is the defining thing that makes it one element or another element, is just how many protons does it have. The electrons could be balanced. If I am a chlorine and I have 17 protons and I have 17 electrons, I'll have no net charge because protons are +1, electrons are -1. But that's not always the case. You can have an imbalance between the protons and the electrons, which we should look at right now. So let's say, let's look at chlorine. Chlorine has 17 protons. And has these electrons on the outside. It might have 17 electrons if it's balanced, but in general, chlorine has a valence shell that only has, I don't know if you remember valence shells, it's the outermost shell of the atom. And there's this octet rule where the valence shell, unless you're like in your 1s or something, is going to be happiest, be most energetically favorable condition if it has 8 electrons in it. So if I look at chlorine and I look at its valence shell, it's got 7 electrons. 1, 2, 3, 4, 5, 6. Whoops. So it's got 7 electrons. It is actually gonna probably grab, if there's any electron lying around or zipping around somewhere, it's gonna grab onto it and hold on to it and add an extra electron. So now all of a sudden, instead of having 17 electrons, I have 18 electrons on the outside. That's just to complete its octet rule. It's gonna be more energetically favorable to have 8 electrons in its valence shell. But now I have a charge imbalance. So what is the overall charge on this chlorine atom?
-1.
-1. This is now a Cl-, which is a type of anion, meaning negatively charged ion. You get a different situation with the things like in the first column of the periodic table where they only have 1 electron in the valence shell. Like for instance, if we have sodium, we have 11 protons. And then if we go into the orbitals of the electrons, the valence shell has 1 electron. The valence, the outermost shell. Again, this is not energetically favorable. This is barely hanging on there. It would much rather just let go of this and then retreat back to the next shell below. So this typically ionizes, it usually lets go of that extra electron. So we're going to be left with 10 electrons on the outside because that 1 valence electron, which is very weakly connected to the rest of the atom, is going to just go find something more interesting to do. Probably end up grabbing onto the chlorine, right? That chlorine was desperately looking for an extra electron and pulling hard. This sodium is barely holding on to this, so it lets go and this electron finds some other adventure to have. So what happens to the overall charge on this thing?
Does it go
+1.
positive?
Positive.
This is going to be a cation
+1.
now, Na+. Now, ion is the generic term for a charged atom. It's a cation if it's positively charged. It's an anion if it's negatively charged. Ions are going to be super important in our class because they are the main ways that you carry electricity in the body. If not is. So an electrical current is the flow of charge. Like in most of the electronics, the flow of current is going to be electrons. You know, in your TV set or your computer or your iPhone, the electrical current that's flowing is from moving electrons. But in your body, there's lots of electricity as well. And the flowing of current, the flow of charge is going to be charged atoms, the ions. So when we're looking at all the electrical properties of your cells, we're going to be talking about electrical currents. And we're going to be talking about these voltages that are driving the flow of the ions, but it's going to be the ions being the things that are, you know, completing the circuit, so to speak. In fact, we're going to see that in the lab today even. You know, ions can complete any kind of electrical circuit. It's just normally in the electronics that you have in your house, you know, it's using the using electrons because it's just cleaner and easier with all the solid state stuff. But ions are just as capable of moving charge from one place to another as well to create electrical current. So ions, hugely important in our class. The other thing we can add into the picture of the atom, just for completeness, is the neutrons. So if we go, let me look, chlorine has 17, so probably about 8. A lot of them will have like 18 neutrons. Some of them instead are going to have like 19 neutrons. What do we call, if I have a chlorine with 18 neutrons versus a chlorine with 19 neutrons, what do I call those different versions of chlorine?
Isotope.
Isotopes.
Those are isotopes. In general, we're not going to be that concerned with isotopes in our class. Although from a standpoint of kind of the clinical applications of things, it's worth thinking about isotopes in how they make the atom stable or unstable. There is a certain number of neutrons that would be a stable isotope where the atom stays and just does its thing, versus an unstable isotope where the nucleus breaks apart. And when it breaks apart, it releases energy and becomes some other kind of element and all that. Those are radioactive isotopes, which are actually really important in medicine because those are the things you use like for imaging to create the radiation, or in like radiation therapies for cancers where you use radiation directed to kill tumors and things. So, you know, unstable isotopes, radioactive isotopes are important in medicine, or for tracking things, like you want to see where things go. Or somebody has an overactive thyroid, you can give them radioactive iodine, which is going to concentrate in their thyroid and kill off their thyroid cells. So radioactive isotopes are clinically relevant, but in our basic physiology class, you should know what they are, but we're not going to talk, you know, past 9:10 today on January 27th. I'm not going to really mention them much more, except they might show up on a test question. So you should know what they are, but we're not going to go deeper into them in terms of their relevance. Whereas the idea of what element is this, Is it an anion or a cation? That's going to be huge. All right. So that is the atom. Then what if we want to make a more complicated thing? So using just atoms, by changing the number of protons, you can make all the different elements. So you got like 92 naturally occurring elements, but you can do lots more fun stuff when you put them together and make other stuff. So, chemical bonds, so molecules. So these are chemically bonded atoms. So it's not just atoms sitting next to each other, like a classic molecule like water. It's not just, oh, here's a hydrogen, here's an oxygen, there's another hydrogen, and they're just in the room together. There's something much more intimate happening. In H2O, so in chemical bonds, there is some intimate sharing of electrons. Like an H2O is a thing. It's not just, oh, here's an oxygen, here's a hydrogen, here's another hydrogen, and they're just having tea together. They have become this like unit where they are intimately sharing electrons. Some electrons are spending some time here and some time here. So it's more, their fates are tied together here. We're going to talk about the two main kinds of bonds that happen between atoms to create molecules. Then we're going to actually talk about one other kind of chemical bond that is super important. That's more about attracting different molecules to each other rather than connecting, doing the fundamental attaching the atoms together in the molecule itself. So what kind of chemical bonds can we use to make molecules?
Hydrogen bonds.
So hydrogen bonds are going to be, they can occur between different parts of a large molecule, or they can more typically occurring between separate molecules. So they're kind of attracted to each other, but that's not going to be the core kind of bond that actually.
Ionic bonds.
So the
Covalent.
covalent and ionic
Covalent.
bonds are going to be the first two that we're going to talk about. Hydrogen bonds are going to be super important, but let's start with the bonds that will actually create the molecules in the first place. So there's covalent bonds. So this is kind of a true sharing of electrons. Like, for water, you have oxygen and it has 6 electrons in its valence shell. And like we said, from this kind of octet rule, it wishes it had 8. It wants 2 more. Hydrogens, on the other hand. So this is instead of the octet rule, there's like a 2 rule because the 1s shell just needs 2 electrons to fill. So these have 1 electron each, and they wish they had 2. So what happens is you can have a sharing. This electron spends some time here and sometimes here. This says sometimes here and here. This spends sometimes here and here. So both of these guys are happy. This is seeing 2 electrons, which it likes. This is seeing 8 electrons, which it likes. So this is an energetically favorable situation for everybody involved. That's a covalent bond. Water in particular, though, so actually we should, before I go continue, does this make sense? You have electrons that are spending some time on one atom, sometimes on the other atom, and in the wash, all the atoms feel their needs are being met for their field valence shells. So this thing is a stable situation and it holds together as a unit. there are different versions of covalent bonds, which are going to be important. In fact, let's look at water right now. Water is covalently bonded, but because oxygen has what's it's called the lone pair electrons, you actually, I kind of drew it like this so it would be easier to see. But in reality, when you have water, the oxygen, you have kind of this, these electrons tend to go on one side, tends to push the hydrogens down, so it's bent. It's not in a line, instead it's bent. I think it's like 107 degrees or something. So it is not symmetrical. And the side that has more electrons on it is going to have more overall negative charge density because electrons are negative. The sides where there's less electrons and more protons is going to have more of a positive charge density. So if we look at a water, we call this a dipole. Dipole meaning it has two poles, two different sides that are not the same as each other. If you look at it from this side, it's more negative. If you look at it from this side, it's more positive. Right, so this is what we would call a polar covalent bond. So there's charge imbalance when you look at this thing from one side to another side. Overall, it's neutral, right? Overall, there's a same number of protons and neutrons. So if you step back far enough, there's no charge imbalance. But when you're up close to this thing, this side is more negative than this side is more positive than the other side. This is going to be critical when you're trying to understand solubility and things like that. So this is a polar covalent bond, as opposed to covalent bonds where everything is totally symmetrical. So for instance, like methane. You have like this hydrogens on this carbon, and this thing just ends up being completely symmetrical. It ends up being kind of like a tetrahedron. It's kind of pyramid. So if I look at it, whatever side I'm looking at it from, I don't see one side having more negative or more positive. It's the same, no matter what direction I look at. This is symmetric. No unequal distributions of charge. This is what I call a non-polar covalent bond. Non-polar because there is no pole. There's not one side or another side to it. You can't look at one side or the other side and say, oh, there's one side versus the other side. Well, no matter, it's like a ball, right? You look, there's no side to a ball. Well, no matter where you're looking at the ball, you're just looking at the ball. As opposed when you're looking at like an arrow, right? If I have like some arrow, I can be looking at the head of the arrow or the tail of the arrow. It's definitely got two sides to it. It's polar. Whereas a ball does not have any poles. It's non-polar. There's no side to it. There's no up or down or back or front. So this is going to be critical when we talk about solubility. So let's look at this right now. In fact, let's talk about hydrogen bonds. We'll get to ionic bonds in a few moments, but let's talk about hydrogen bonds. So are there any questions about covalent and polar versus non-polar covalent?
So when you say this is critical when you're talking about sorry, you just said this is critical when you're talking about osmosis? No.
Solubility, I think.
Solubility. There you go.
Yeah, whether or not something is going to dissolve in water.
Okay. And what's critical is whether it's polar or non-polar.
Exactly.
Okay.
And I'm going to talk about explicitly why that is the case right now. And it's all going to be about hydrogen bonds. So let's take a look at this right now.
I have a quick question.
Sure.
You said that the polar covalent bond is dipole. Is there an opposite word for the non-polar covalent bond that's like opposite of dipole?
Non-polar.
Just non-polar covalent bond.
Yeah, or it's a
Okay.
non-polar meaning there are no poles. There's no one side or another. Dipole means there are two different sides to it.
Right. Okay.
All right, so hydrogen bonds. Hydrogen bonds are a little different from this bond we were just talking about, because this is typically between two separate molecules. Or it can be between different areas of a very large molecule. But these are not the bonds that are kind of constructing the basic structure of the molecule. This is actually how water stays as a cup of water, right? If I have an H2O, and again, I talked about how one side is more positive, one side is more negative, and that this thing here is held together by covalent bonds. It's a polar covalent molecule. I have another water molecule. Here's another one over here. It's also got. How come if I have obviously I can have a glass of water, those water molecules don't all just go off into the air as steam immediately or something. Why do they all stick together as a cup of water? What's holding all those water molecules together so they stay as a liquid in your cup rather than just become like some gas filling the room?
Is it a double bond?
It's the positivity in the hydrogen is attracted to the negativity in the oxygen. And it's forming a bond between the two molecules.
Exactly. So there's going to be this kind of electrostatic attraction. That's the hydrogen bond. So it's not a sharing of electrons or anything anymore. It's just we have these two dipoles. One has a side that's kind of more negative. One has a side that's more positive. And the more negative and more positive sides get attracted to each other by that electrical, opposite charges attract. This is what's holding waters to waters. An analogy, think about, maybe it's easier to think about magnets, right? If you have, a magnet with a north and a south pole, and you add another magnet in the mix, it's going to spin around and the south is going to be attracted to the north. And I put another magnet in the mix. The south, they're all going to get stuck onto each other based on their magnetic attractions. If I take like 100 of these things, they're going to be a big ball of magnets all stuck together, right? But they can rearrange, right? If I go and I grab this ball of magnets, I can squeeze it and pull it. They're all going to keep holding on. They'll let go of one and grab onto another. They'll stay as a big blob of magnets, but which magnets attached to what magnet, that might be changing as these things shift around. It's the same thing with water in a cup of water. each of these water molecules is going to be attracted to another water molecule by this electrostatic attraction, which we call a hydrogen bond. And usually you do it as little dots. You don't do it as a line. When you do a line in a chemical diagram, you actually mean a covalent bond, an actual sharing of electrons. And this is just an attraction due to this charge imbalance. So we use actually little dots to say this is not a covalent bond. This is just a hydrogen bond due to this attraction. So if I have a whole glass of water, and again, everything in your body is basically dissolved in water. Whoops. This all gets attracted, like the more positive sides of the hydrogens get attracted, the more negative sides of the oxygen here. And the more negative side of this one is getting attracted to the more positive side of this one. And the more positive side of this one is attracted to the more negative. So you've got all of these hydrogen bonds happening. It may make, this is like a water molecule, this is a water molecule, this is a water molecule, this is a water molecule. So they're all attracted to each other and doing this dance with each other. And you can maybe like a square dance, do-si-do, let your partner go, grab another partner, going around, right? They're not like committed to one molecule or another water molecule. They just want to be kind of in the mix and in this big kind of cuddle puddle with each other, holding each other and letting go of one and grabbing another. So that's what a glass of water looks like, or that's what any kind of liquid water is like. We call water is a polar solvent. Solvent meaning it's the stuff you're dissolving stuff in. Polar in that it's a polar molecule that's being held together like this. So then we can ask ourselves, what happens if you put different kinds of solutes into here? A solute is the thing that you're trying to dissolve, right? The terminology, in case you don't remember the terminology. There's the overall stuff. Actually, I actually want to do this one. The main kind of molecule that is around is our solvent. Almost always in our class, in our body, we're going to have the solvent, the overall stuff going to be water. And then the stuff that you are putting in there in much lower quantity than the solvent, that's going to be my solute. And again, like I said, water is a polar solvent because it is there's polar molecules connected to each other by hydrogen bonds. And let's talk about different kinds of solutes. Let's say my solute is a polar covalently bonded thing, like for instance, sugar. So sugar is a polar covalently bonded molecule. We're going to talk more about specifically what about sugar makes it polar, actually in the lab a little later today. But it's going to be hydrogens and carbons and oxygens connected together with covalent bonds, but there's going to be a charge imbalance depending on what direction you look at it from that will make part of it more positive, part of it more negative. What's going to happen if you put a polar molecule in a polar solvent like this?
It'll dissolve.
It's going to dissolve. Why is it going to dissolve?
because it's soluble in water, hydrophilic.
Say it again.
It's soluble in water because it's hydrophilic.
So hydrophilic is the definition that it dissolves, that it likes water. But that's not, so hydrophilic means water loving. So that's going to be the definition of something that acts like this, but it doesn't tell us why. I want to know, why is it hydrophilic? Why does
Because of those, because it's polar, which means it has a charge, it's gonna be attracted to those polar parts of the water molecule. So that positive.
exactly. So
Like,
water,
like,
so like the water is going to want to attract to this polar molecule, and the polar molecule wants to attract to the water. So now it's just part of the dance, and that little do-si-do, let your partner go. It's like the water lets go of the water. Oh, it's grabbed onto a sugar, and the sugars let go of another sugar and grabbed onto a water. So the sugars and the waters are happy being dance partners in this kind of big electric static attraction dance in the water, right? So in fact, let me bring up, hold on one sec. This is something from a PowerPoint thing that one of my colleagues, Eric Dunmeyer, made and was gracious enough to lend me here. Right, so here, this would be a solution. We have a solution. Each of these things that look like Mickey Mouse is a water molecule. The red is supposed to be the oxygen, the white are the two hydrogens. So the solvent, the thing in, it's everywhere. The solute here is going to be these purple things. So this would be a solution. A solution has, in this case, water, and then some things sitting in there. Solvent is the stuff. Solute is the stuff that is in lower amount that you're adding in there. So this is a solution. And now we're going to talk about what is the difference if that solute is polar versus non-polar in this water, this water. So let's say the solute is a polar covalently bonded thing. It will dance. It'll dance here. This, in fact, let me get my little annotation tool here. If I have a polar molecule here, it can grab onto a water. The water can grab onto this. It can attract and let go. So if it's a polar solute, it's going to be hydrophilic. It'll be water loving, so to speak. It will dissolve in water because both the water molecules and the solute molecules will be attracted to each other and do this dance. What if I have a non-polar solute?
It will not dissolve in water.
And why is that?
Because there will be
There's no charge.
attraction.
There's no electrostatic charge, so there's nothing to bond to.
There's no attraction to the water. The water is still pulling on itself. It's all happy to grab onto itself and do its little dance. The solute is going to be ignored. It's not going to be part of that at all. It's just going to get squeezed off to the side. So does not, dance with the polar water molecules. We say that it is hydrophobic, which means like water fearing. It will not dissolve. It will not kind of go into solution. This word is a little, what's the right word? Deceptive. It's not really true. Phobic, it sounds like it's afraid of the water, right? If you add oil in water, oil is a classic non-polar molecule. Obviously, when you add oil and water, they don't mix. The oil separates if you try to mix them. It looks like the nonpolar thing is afraid it's getting away from the water, but that's not really what's happening. Instead, it's just the water is pulling on itself and kind of squeezing this nonpolar thing off to the side, right? It would be like if in our class, everybody was in this whole big cuddle puddle trying to like hug each other, and then like somebody walks in and we don't like them at all, and everyone's ignoring them. You know, in fact, we don't even know that they exist. They walk in and we're just so focused on giving everybody else a group hug, they just get squeezed off to the side. But it's not like anything is afraid of anything. It's just that when you try to put a nonpolar solute into water, the water molecules are all just hugging each other, and these nonpolar things just get squeezed out to the side. So this is going to be critical in physiology, though, understanding if a solute is polar or nonpolar. For instance, as a class, lipids tend to be nonpolar, which means they don't dissolve in water, like fats, which means if you want to carry fats around in your body, which in your bloodstream, they don't just dissolve. You're going to have to come up with special systems to actually transport fats and cholesterols around in your body. Fat soluble vitamins, there's a number of vitamins that are nonpolar, and you can't just dissolve them in the blood and move them around. Certain hormones, like the steroid hormones, estrogen, testosterone, they're nonpolar. They don't dissolve in bloodstream and just move around. You're going to have special carrier molecules to actually move them around. So knowing whether something is polar or nonpolar, whether it's hydrophobic or hydrophilic, whether it's going to dissolve or not dissolve in water, is going to be super important, for the next 4 months. So hydrogen, let me go back. Hydrogen bonds, again, can be, like we just talked about, between separate water molecules, between the water molecules and the solutes. Just for completeness, hydrogen bonds can also be between different parts of a large molecule. Like if you, like some proteins that have, like they can have tens of thousands of amino acids connected in big long chains. You can actually have different parts of a large molecule kind of held to another part of a large molecule by hydrogen bonds. So hydrogen bonds can be between different areas of a large molecule. Actually, a classic example in DNA. These are hydrogen bonds that are creating the attraction between the nucleotide bases and the base pairing. Those are hydrogen bonds inside a large molecule. Or often in proteins, you have hydrogen bonds kind of stabilizing the structure of this big, complicated folded snake. So hydrogen bonds can also be between different parts of a very large molecule.
So if it's a hydrogen bond within a larger molecule, the larger molecule is still classified as a hydrogen bond.
No, because it's not, it's going to be mainly covalent bonds that are connecting the different parts of it. But then the hydrogen bonds are helping kind of maintain its shape or holding different parts of it together. But hydrogen bonds aren't that strong. Think about water. If you take a cup of water, you can smash apart those water molecules into little splashy droplets like that. Hydrogen bonds, they form, they hold, but they break apart pretty easy as well. Covalent bonds are much more solid. Like breaking a hydrogen bond is pretty easy. You can do it by slapping it with your hand. Breaking a covalent bond is not so easy. So what we're gonna do is just finish tying off this chemical bonding thing and get into the lab stuff. So let's. So covalent bonds, we just talked about one way to connect one atom to another. We talked about how they can be polar covalent bonds, which means that they are going to also be hydrophilic, meaning they'll, like water, they'll form hydrogen bonds with water and dissolve in water. There can be non-polar covalent bonds, which are going to be hydrophobic, meaning that they don't form hydrogen bonds with water and appear to be afraid of the water, even though it's a bit of a misnomer to call them phobic, more like don't like to play with the water versus being afraid of the water. So the other bond that we need to talk about are ionic bonds. And these are also a sharing of electrons, but whereas covalent bonds was a sharing, covalent bonds, there's a sharing of electrons, even if it's unequal sharing, it's still sharing, like one's holding more or less, or maybe they're both holding the same amount. But the electrons are always hanging out with the atoms involved with the bond, and it's all one big happy family, one single entity. Like an H2O is always an H2O, and they stay stuck together, and for better or for worse, those two hydrogens and that oxygen are kind of zipping around and having their adventures. Ionic bonds are pretty different. Ionic bonds are when you have one atom, or it can also be a molecule. You can have ionic bonds between molecules. You have one piece give up completely its electron and another one completely accept the electron. So like the classic example is like table salt, sodium chloride. Talked about sodium having that one valence electron that it's barely holding on to, and chlorine having 7 valence electrons, and it so wants an extra electron to complete the octet for its valence shell. So two things are happening. The sodium is ionizing. So now we have an Na+, and at the same time, there is a chlorine that's desperate for an electron, and it's grabbing an extra electron. So we have a Cl-. And so now we have these two ions. This isn't just about charge imbalance like in covalent bonds. This is like ionized. This has got a charge on the actual entity. This is a plus Na. This is a negative chlorine. And I should also mention, I'm realizing now as I'm writing these things on the screen, obviously Na doesn't look like sodium, right? Na, it means natrium, it's like Latin. Some of these symbols we're going to be using a bunch. You need to just, if they're not already, like in your brain is this automatic translation, they need to be, because I'm going to spend so much time just writing Na plus usually. And you just got to think immediately in your mind, oh, that's obviously a sodium. You shouldn't even have to translate it like Na, what's Na? Na is like, oh yeah, so it should just get instantly, Na is a sodium. The other weird one is potassium. Potassium is K. Or is it the other way? Whatever. Whenever you see a K, it's a potassium. It should just be instantly translated, because I will be writing Na plus and K plus on the screen right now or on the board once we're in class constantly till the end of the semester. They are some of the main ions that are involved with cellular signaling and stuff like that. Other chemical symbols are not as confusing. You know, Cl is chlorine, Mg is magnesium, things like that. So Ca is calcium. You know, some of these things ionize, but they ionize with 2 electrons. Like magnesium and calcium, we're going to see them quite a bit as well. But when I have a calcium, it's got like 2 electrons that are loosely held in its valence shell that are going to disappear. Meaning, what is my calcium going to be that's left?
2+.
It's going to be 2+. You can write it either Ca2+, or I usually write it like that, Ca++. But we'll see calcium as a +2 cation all the time. Okay, so back to where we were. Ionic bonds. Sodium, when you put it in water, it's basically going to let go. It's going to just be Na plus. This is not even just in water, just hanging out. It's Na plus Cl minus. And now there is this really strong electrical attraction between these two, right? If you have this thing that's totally plus and totally minus, these are going to have this attraction and they're going to pull on each other. You know, that's the classic ionic bond. They're pulling on each other because one has ionized, the other one has grabbed an electron. You know, have a plus and a minus thing that then are pulling on each other because of their opposite charges attract. A thing, though, that's really different about ionically bonded things than covalent is this sodium ionizes. It gives up the electron. It's not tracking where the electron goes. It doesn't care. It just let go of it and it's gone. This chlorine really wanted an electron, was reaching and grabbing. It found an electron, became a Cl minus. It doesn't know where that electron came from. There's no like deal or commitment between this sodium and this chlorine that they are like meant for each other. It's just like the sodium is plus now, the Cl is minus because they either spit out an electron or grabbed an electron from wherever. So an NaCl is not really an entity like a H2O would be. Instead, you end up getting what we call like a crystal lattice. You know, we have our Na pluses, and the Na plus is going to be attracted to Cl minuses. But the Cl minuses are attracted to Na pluses, you know, which are attracted to Cl minuses. You know, so you just get this big crystal lattice of anions and cations assembling in this big crystal. No sodium or chlorine is necessarily attracted to any other particular sodium or chlorine. It's just more as a rule, sodiums are attracted to the chlorines are attracted to the sodiums, and they all arrange in this big crystal. This is going to be really important when we look at the difference between putting ionically bonded compound in water versus a polar covalent compound. So what happens? I have my salt crystal here. What happens when I take this salt crystal and I put it into water? Is it going to dissolve, first of all?
Yes.
It will dissolve. There's lots of pluses and minuses to dance around with the plus and minuses of the polar water molecules. How is it going to be different than putting like sugar into water, for instance?
Because the sodium and the chlorine, won't they disassociate into ions?
Exactly. So this sodium here, it has no commitment to this chlorine or that chlorine or whatever it's connected or attracted to in the lattice. It's just as happy to be dancing with the water molecules once it goes into solution. So this whole thing just disassembles. You end up having individual sodium ions just floating and making hydrogen bonds with the water. And you have individual chlorine molecules going off on their adventure, so you end up having what we call dissociation. It's not, so it will dissolve. Let me maybe put on a new page so these ionically bonded compounds, they dissolve in water, but they do more than dissolve. They don't just dissolve and go into solution. And they also what we call dissociate. Right, so this is super different than putting sugar in water. When you take a sugar cube and put it in the water, the individual sugar molecules are going to find their own adventure. They're no longer going to be all connected to each other sugar molecule in the sugar cube or sugar crystal, but the sugar isn't going to fall apart, right? If I look at a sugar molecule, it's got oxygens and hydrogens. Let's just say it's a bunch of oxygens and hydrogens. I can't even draw one completely from memory, so you don't need to either. But it's these oxygens, carbons, hydrogens, all kind of connected together as a C6H12O6. This is like a glucose, for instance. When you put this in water, it will dissolve because this thing is polar, like wherever you have like hydroxyls and stuff, like you have like, I should just show you, like if you have like, whenever you see an OH hanging off, it's a really common group that make up molecules. Whenever there's a hydroxyl, hydroxyls are like a giveaway that this thing is polar, because OH, it's not actually an OH, it's an O connected to an H. So it's actually like, if here's my carbon, I'm going to have like a oxygen and then a hydrogen coming off of that. And then whenever I see an oxygen is going to have its lone pair of electrons. So it's going to be minus, the hydrogen is going to be more positive. This oxygen here is going to be more. So whenever hydroxyls though, and oxygens and hanging out in rings like that, those are always signs that you're going to have charge imbalance, that this thing is going to be polar. So I put my sugar into water, it dissolves, it goes into solution because it's a polar covalent molecule because the hydroxyls and the oxygen and stuff. But the core integrity of this thing in terms of just being a single unit, being a C6H12O6, that stays intact. That does not come apart at all. It went in as a single unit. It's dissolved and doing its little dance with the water molecules, but it is staying intact as a single unit. Whereas I put my salt crystal in there, is totally different. This thing that had NaCl's is now a bunch of NAs that are doing their own thing, a bunch of Cl's doing their own thing. There's nothing left that is like a single unit, an NaCl. It's not till you evaporate all the water and they find each other again and reassemble in a crystal that you've got something that you'd call like a salt crystal again. So that's going to be super important distinction when I look at covalently bonded things. They're going to dissolve, but they do not dissociate. They stay intact. Whereas an ionically bonded compound is going to dissociate into independent ions in addition to dissolving. Now, you're not going to see it with your eyes. From your eye, which we're going to look at in the lab in a few moments, it's just going to look like they dissolve. You put salt in water, it disappears, it dissolves. You put sugar in water, it disappears, it dissolves. But at a kind of molecular level, there's something super different happening. In fact, let me go to back. Now I can show you the stuff from Eric's PowerPoint. So here, this is showing what would it be like to take like table salt. Here in this little picture, the little Mickey Mouses again are water molecules that are making up our solvent. The green are the chlorine with minus charge, the anions, Cl minus. The little plus yellows here are the cations, the sodium ions. So you put this crystal, when it's just a crystal of table salt, they're attached to each other. But as soon as you go into water, the pluses are no longer just stuck to where they were. They're happy to find a new dance partner here. So now all of a sudden, this little sodium here is dancing with these water molecules. This doesn't care if it's a chlorine anymore. This chlorine, it's got found new playmates here, electrostatic attraction with the polar water molecules. So this thing is just going to start dissociating, coming apart. And so here you can see it's more and more of this disassembling of this crystal lattice until ultimately you just have ions, anions and cations independently finding their way dissolved in the water. From looking at this, you can now see we have independent charges floating around. Like a sugar molecule is not charged. Remember I said overall a sugar molecule is polar. It's got an imbalance from one side to the other, but overall it's a neutral thing. Here now though, we have something super different. When we look at, let me get a different color here. We look at this chlorine, it's a charged atom, it's an anion. We look at the sodium, it is a cation, which means these can now carry electric current. Remember, electric current is just flow of charge. That means if there is some voltage, there is some electrical pressure, I can actually have electrical charge flow from one side of the solution to the other. It means I can use this to complete an electrical circuit. So let me show you that. That's also going to be part of our lab today. If you take pure water and you put these wires in here trying to complete a circuit, it's not going to work. But if you use salt water between the wires, it's going to light up. In fact, you're going to see that. I mean, unfortunately, you're going to see videos of us doing this and, we recorded instead of doing it yourself, which is really fun. But we will be back in the lab soon. Sugar, you put sugar water and you put the wires in, there is no electrical current because the sugar molecules are not charge carriers. They're not actual charges that can move. Each sugar molecule is neutral. It doesn't have an overall positive or negative charge. It just has a charge imbalance that allows it to dissolve. So does that make sense? So let me stop sharing this. Where's the time? Okay, let me just. So super important concept, electrical properties of, or electrolytes. With electrolytes or is another name for these things that are ionically bonded compounds. And they get that name because they carry electrical currents and they donate electrical charge when you dissolve them in water. Obviously, sodium, and chlorine, sodium chloride table salt is a ionically bonded compound. In general, how are you going to decide whether something is likely ionically bonded versus covalently bonded? Because you are going to have to actually, it makes a difference in how it behaves. So you actually are going to have some basic sense of when is a compound ionically versus covalently bonded. Anybody?
Are ionic bonds typically when you have like a salt and a metal mixed together?
Yeah, well, so this thing is a salt, but yeah, so usually it's, if you have like one of the alkali metals, like here, if we go back to the periodic table here. These are like the alkali metals. These are the ones like sodium, potassium. These are everything in this column of the table has one valence electron and is very likely to ionize into a cation. Same thing here is column 2. These are the things that also, these have 2 valence electrons, very likely to ionize to become a +2 cation. So when you have things with like lithium, sodium, or potassium, magnesium, or calcium, you look at these suspiciously, depending on their situation, they are likely to ionize or have a good chance. Then you look here, this column, the halogens, chlorine in particular. When you have this chlorine, this is a thing with these 7 valence electrons. So if I have something that's sodium chloride, I am almost sure that this thing is going to be ionically bonded because I have this thing that really wants to give up an electron and this thing that really wants to grab an electron. Same thing with potassium chloride or lithium chloride. What about calcium chloride? It's another ionically bonded compound, except what's going to be the chemical formula for a molecule of calcium chloride?
CaCl2.
Yeah, because this calcium is going to give up 2 electrons, which means we need 2 chlorines to grab 1 each. It also means if you're looking at NaCl, kind of in an aqueous solution, it's going to ionize into what?
Sodium and chloride.
Sodium N+ and Cl-. If I take calcium chloride, what's it going to turn into when I put it into water?
Ca2+ and Cl-.
More precisely?
Cl-.
Yeah, 2 Cl-. So it'll have 2. So this is going to be important when we get to what we call osmolarity. Like next class, I'm going to get much more into how we specify concentrations. Each NaCl becomes 2 particles in the water. Each calcium chloride becomes 3 particles. How about if I take a sugar, how many particles does a sugar become if I put a sugar molecule into water?
1.
It becomes 1 because the sugar doesn't break apart. So when we get into what we call osmolarity, how many actual particles are in the solution that are influencing osmosis, it's going to be actually super important that you understand for any particular solute Does it not dissociate at all? In which case there's a 1-to-1 proportion between molecules and particles. Does it dissociate into 2 pieces? In which case you've got twice as many particles as molecules. Does it dissociate into 3 pieces? In which case we have 3 times as many particles as molecules. So next class, we're going to look at this in way more detail, but just kind of introducing this so you know that this is going to be important. Like if you make a mistake here, you can really mess up your concentrations of like what kind of things you're going to infuse in an IV. And instead of helping somebody, you're going to explode all of their cells in their body, in their blood. You know, so it really makes a difference to understand if it dissociates or not. So to finish this up, I saw somebody posted something in the chat, which I think is a really useful thing to say for everybody. Whoops, I didn't mean to do that. This idea that like dissolves like. Meaning, if I have, so it means a like solvent dissolves a like solute. So if I have a polar solvent, you know, for instance, water, you know, this will dissolve polar solutes. Not nonpolar. So if I have a polar solvent, solutes that are polar will dissolve in it, but not nonpolar. So we've already talked about this. Polar solutes like sugar or salt will dissolve in water. Nonpolar things like oil or, you know, cholesterol will not dissolve in water. However, if I have a nonpolar solvent, you know, like oil or gasoline or something. These are nonpolar solvents. You know, the solvent molecules are just kind of sitting on top of each other. These tend to evaporate, not always. So gasoline, oil, if these are going to dissolve nonpolar solvents, I mean solutes, I should say, sorry about that. So if I take oil and put it into gasoline, it will dissolve in there because basically none of the molecules are polar, so they all just kind of intermingle with each other. Nobody's more or less attracted to anybody else because nobody's attracted to anybody. So they all just kind of intermingle. If I put a polar solute in there, it's not going to dissolve. I mean, I don't know if it's still something like one of the really sucky things you could do to somebody used to be like putting sugar in their gas tank. What's going to happen if you put sugar in gasoline?
It won't dissolve.
It won't dissolve. The sugar molecules are polar. They're just going to keep holding on to each other. There's nothing in the gasoline that is making them attracted and kind of tempt them away from just staying in their sugar crystal. So basically you have little rocks in your gas tank that, you know, probably in the older engines that didn't have as good filtering and stuff would get sucked into the intake and grind up your cylinders and stuff. So if you take sugar or salt and put it in oil or gasoline or some other nonpolar solvent, it will not dissolve. So this like dissolves like is a classic and it's useful. So I would say you should make sure you should know this, you should be able to say it, but you should know what it means as well. So yeah, whoever shared that, thank you. Okay.